Greetings and welcome to the 5th episode of PHS Physics SOS. Today I'm going to be going over the first worksheet on projectile motion, which covers part of Chapter 3. So the first question reads, you accidentally tap a nickel so that it flies off your 1 meter high desk. How long will it take the nickel to hit the ground? So we're going to draw a picture. This is 1 meter high, and it falls. So we want to know how long this took to fall. So we're going to use the equation delta y equals v naught t plus 1/2 at squared, because it's going to be the best option to find our time from the distance traveled. You could use other equations, but you'd have to use multiple equations. This is the easiest way to do it in one step. So there's no initial velocity because it's dropped, so by definition your initial velocity is 0. We know our delta y is 1. It says 1 meter. I mean, it fell 1 meter, but you have to be careful since it's falling, starting from a high position and going to a low position. It's actually -1 equals 1/2 a, so 1/2 of gravity, so -4.9 t squared. So you're going to move the 4.9 over, take the square root, and get your time, which turns out to be 0.45 seconds. Now question 2 reads, if the nickel lands 1.2 meters away from the bottom of your desk, what was its horizontal velocity? So now they're telling you that it didn't actually fall like this, it fell like this, where this was 1 meter and this is 1.2 meters. So we know that this fall, however it may have went, took 0.45 seconds. Now we want to find what the horizontal velocity was to get it 1.2 meters away in that same time. So we're going to use velocity equals distance over time, and this isn't a formula you should really have to memorize because velocity is expressed in a unit of distance, so like meters, over a unit of time, like seconds. So just by looking at the units of velocity, I mean, you can have miles per hour, kilometers per nanosecond, feet per day. I don't know. There's an infinite number of units, infinite number of combinations. It's just any distance over any time. So you really shouldn't have to memorize this. You just look at the units and think, okay, well, I have a distance and I have a time, and velocity is in distance over time, so I'll just take the distance and divide it by the time. So 1.2 over 0.45, this is meters, this is seconds, and you get 2.7 meters per second. The next question is question 3. And question 4, which are very similar to question 1 and 2, just different numbers. It says, the little boy throws a rock off a 30-meter high cliff in La Jolla. How long does it take the rock to reach the ground below? So we draw our picture. And I'm just going to go ahead and read question 4 so I can draw it accurately in one step this time. Question 4 says, if the rock lands 4.7 meters away from the base of the cliff, what is the initial horizontal velocity the boy threw the rock with? So the rock kind of falls like this. And this is 30 meters, and this is 4.7 meters. So for the first part, since we know it's being accelerated by gravity, we're going to use the equation that has accelerated displacement relative to accelerated motion. So delta y equals v naught t plus 1/2 at squared. So delta y is -30 equals, there's no initial velocity, at least in the y direction, we have to assume, plus 1/2 our acceleration, which is 1/2 gravity, t squared, so -30 over -4.9, take the square root to get our time, which is 2.5 seconds. And then question 4, wants to know what the initial horizontal velocity was for it to get 4.7 meters away in 2.5 seconds. and I probably should have mentioned this in the last problem, but the reason we're using different equations for the vertical displacement and the horizontal displacement is because the vertical displacement is accelerated. It's being accelerated by gravity, and gravity only accelerates you up and down. You don't see gravity pulling you to one side or pulling you to the other side. It's only moving you up and down. If you jump on unmoving ground, you're not suddenly, I mean, you're going to fall back down, but you're not going to like fall over here or fall over here. So the acceleration is only in the downward direction. In the horizontal direction, there's no acceleration because there's an initial velocity and then it doesn't change. Technically, there's air drag slowing it down, but we're ignoring that. Okay, so to find our initial horizontal velocity, we're going to take the total horizontal distance traveled over the time it took to get our horizontal velocity, which is going to turn out to be 1.9 meters per second. And if you want to give that some kind of name, you call it v sub x. The next question is question 5, and it says you roll a ball bearing along the surface of the 1.4 meter high counter at a rate of 1.7 meters per second. When the ball hits the floor, how far will it have traveled horizontally? So first we draw a picture, have our table, and it is 1.4 meters high. It's too small. 1.4 meters high, and we have a ball bearing getting rolled off of it with an initial horizontal velocity. So this is our x velocity. Almost all the time you're going to see horizontal velocity referred to as your x velocity because, I mean, if you draw a graph, y is up and down and x is back and forth, so it's just easy to remember. But I mean, if you want to, you could call it v sub h for v horizontal or whatever. But v sub x is easiest to recognize. So the horizontal velocity is the rate at which it's being rolled along the counter, which is 1.7 meters per second. And the reason that's your horizontal velocity is because we can agree that, I mean, we assume the counter's level, so it's only moving in the horizontal velocity, and the horizontal direction, and he's pushing it at 1.7 meters per second. So when the ball hits the floor, how far will it have traveled horizontal? Oh, okay, so first we need to figure out how long it took to fall. So question 5 is kind of like, it's very similar to question 1 and 2 and then question 3 and 4, but it's just kind of asking you for, I guess this is all similar stuff, never mind. So first we need to find out how long it took to fall, so we want an equation with time in it and our height, because using just time and height and acceleration that we know is gravity, using just height and acceleration we can find the time, so we're going to use delta y equals v naught t plus 1/2 at squared, and there's no initial velocity. But wait, this is an initial velocity. No, it's not. It's only horizontal velocity. And this equation is dealing specifically, because we're using delta y, this equation is dealing exclusively in horizontal motion, and this is, exclusively in vertical motion, and this is a horizontal motion. So we're going to start plugging things in. Negative 1.4 equals 1/2 a, negative 4.9 t squared. Move everything over. Equals our time, which is going to equal 0.53 seconds. And then we want to figure out how far horizontally it traveled in that time. So we want to find our delta x. And since there's no horizontal acceleration, we're just going to use delta x equals vt. So that's going to equal 1.7 times 0.53, which is going to equal, 0.91 meters. Now question 6 asks, what will the final horizontal velocity of the ball bearing be from problem 5? And as I was saying, the horizontal velocity is not accelerated, it's just constant. So the final velocity, the final horizontal velocity, and the initial horizontal velocity, and the horizontal velocity here, or here, or here, they're all going to be the same thing. 1.7 meters per second. So that's just a conceptual problem. No math needed. Now question 7 asks, what will the final vertical velocity of the ball bearing be just for, sorry, reading the wrong problem. Question 7 says, what will the final vertical velocity of the ball bearing be just before it hits the floor? So for this, we're gonna want to use velocity equals v naught plus at. And since this is only vertical velocity, there is no initial velocity. The only initial velocity we had was horizontal. So our final horizontal velocity is going to be equal to our acceleration, which is negative 9.8, times our time, which is 0.53 seconds, which is going to give us negative 5.2 meters per second. Now, question 8 is going to ask us, what will the final resultant velocity of the ball bearing be just before it hits the floor? So, we know that its final horizontal velocity is 1.7 meters per second, same as the initial, and we know that its final vertical velocity is negative 4.2 meters per second. So, horizontal is 1.7, and vertical is negative 5.2. These are vectors, right? So we just draw our resultant vector. And to figure out what that is, we use Pythagorean theorem. So we're going to do the square root of 1.7 squared plus negative 5.2 squared, which is going to give us 5.5 meters per second. So that's the magnitude of this vector, and now we need a direction. So we're going to take the inverse tangent. So we want this angle. The inverse tangent of opposite over adjacent, so negative 5.2 over 1.7. So inverse tangent of negative 5.2 over 1.7 is negative 71.9 degrees. Now the reason that's negative is because we gave this a negative value, which is kind of funky when you're doing trigonometry. So it really just means this angle is below the horizontal, because if we define this as negative, meaning it's below where it started. So the angle, so we're just going to say 71.9 degrees below the horizontal. Can't spell. And please don't say south of east. It's horizontal and vertical. That's for different stuff. The next question is question 9, and it reads, Mr. McMurray retires and goes on an ocean cruise. He plays shuffleboard on the back of his ship. While it is tied up at the dock, he accidentally shuffles his puck off the back of the ship. The puck flies horizontally 2.9 meters for 1.62 seconds before hitting the water. What was the initial horizontal velocity of the puck? So, that's a lot of information. So here's our ship. That's a bad looking ship, but whatever. So the puck flies backwards, and this is 2.9 meters, and time is 1.62 seconds, and it wants the initial horizontal velocity. So again, this is just non-accelerated horizontal motion. Well, horizontal motion is never accelerated, so it's just non-accelerated motion. So we're just going to do distance over time. 2.9 meters over 1.62 seconds equals 1.8 meters per second. The next question asks, how high above the water is the deck where the shuffleboard is located? And so we know we know how long it took to fall. well, we know how long it took to travel this distance, but it was also falling during that time, so then we know how long it took to fall this distance. So this is going to be our delta y, which is now what question 10 is looking for. So we're going to use delta y equals v naught t plus 1/2 a t squared. Delta y is our unknown. There's no initial horizontal velocity. There is an initial vertical velocity. Sorry, backwards. There's no initial vertical velocity, y velocity, but there is an initial horizontal velocity, or x velocity. But we're dealing in terms of y right now, so there's no initial velocity as far as we're concerned. Another way to write this, if it confuses you, when there's delta y, you can do v initial y, like through your initial, whether it be a 0 or an I. So like you do like v I y. So this is v initial in the y direction, or this could be, well, I guess it's always constant, but you could use v initial in the x direction, even though it's always constant, so that doesn't really mean much. But this is just another way of notating it to make it a little maybe easier to understand what you're doing. Okay, so we're going to set delta y equals 1/2 a negative 4.9 times our time squared, which is 1.62 seconds. 2 seconds squared, sorry. Then we plug that all in, you get negative 12.9 meters. That's your delta y, but it's asking how high above the water is the deck. And the deck's not negative 12.9 meters above the water. That would make it below the water. It's just 12.9 meters. So you don't need the negative sign, even though your answer is negative. You have to be able to interpret your answer and make it match what the problem is actually asking for. Now the next question, question 11, says, what is the final vertical velocity of the puck? So vertical, again, is our y velocity. So v vertical, or v sub y, and it wants final. So that's going to be equal to v final equals v naught plus at. Again, since we're dealing in terms of y, there's no initial velocity in this case. Equals negative 9.8 times our time, which is 1.62 seconds, which is going to turn out to be negative 15.9 meters per second. And it's important you have the negative in here with the 9.8, otherwise you'd get positive 15.9 meters per second, which would mean it's going up at 15.9 meters per second, which really wouldn't make any sense because it is falling off of a boat. Question 12 asks, what is the horizontal velocity of the puck after 1 second? Again, this is another conceptual trick question, kind of. It shouldn't really be a trick question. But remember, horizontal velocity never changes, so it's just going to be the same horizontal. Horizontal is x velocity, horizontal this direction, x this direction. So it's just going to be the same as this. Same as our initial, same as our final, for horizontal at least. So 1.8 meters per second. And question 13 says, what is the vertical velocity of the puck after 1 second? So, to find that, we're going to use our y velocity equals our initial y velocity plus acceleration times time. So, we want, there's no initial velocity in the y direction, otherwise known as a vertical direction. So it's going to be negative 9.8 times 1 second. So it's just going to be negative 9.8 meters per second. I guess I should box all these. Now, question 14, hang on, a new piece of paper. Question 14 reads, what is the vertical position of the puck after 1 second? So vertical position is our up and down position, our y position. So it wants y when t equals 1, and this is problem 14. So So we're going to use this handy dandy equation, delta y equals v naught t plus 1/2 at squared. There is no initial vertical velocity for this problem, so our delta y is equal to 1/2 a, which is 1/2 negative 9.8, which is negative 4.9. T squared, t is 1 squared is 1, negative 4.9 times 1 is 1. So our delta y is just negative 4.9 seconds. And yes, this should be meters. I said seconds, it should be meters, negative 4.9 meters. And this should be negative because it's asking for the position, and since it fell off the boat, the position is going to be negative because it went from higher to lower. Question 15 reads, Miss O'Brien goes cliff diving in Acapulco. She leaps off of a 15-meter cliff in a perfect swan dive. Sure, Cobb. She lands 3.2 meters away from the bottom of the cliff. What was her final vertical velocity? So first thing, picture, we have our cliff, we have it's water, deal with it. So Brian's going to be a particle because we don't know how to deal with air drag. This is 15 meters high, and this is 3.2 meters away. So it wants final vertical velocity, so v final in the y direction. And something to note about this problem is that we don't have time. So what equation are we going to use when we don't have time? The timeout equation. So our v final squared, and mind you, for the timeout equation in this case, we're only analyzing the y direction. So we're doing v final of y squared equals v initial of y squared plus twice the acceleration times delta y. So this is what we're looking for. So v final y squared equals, so there's no v initial in the vertical direction. Twice acceleration is negative 19.6, and delta y is 15 meters. And when you multiply those out and take the square root, hang on, let's see, negative 19.6 times 50. Oh, sorry, this should be negative 15 because it's a delta y and it started high and ended low, so it's a negative displacement. So I was wondering how I was going to take the square root of a negative number. So you get 294, take the square root, and we get v final y equals 17.1 meters per second. But wait, when you take the square root of a number, you're always going to get a positive number, but in the process of getting a square number, you could either have a negative or a positive number. What I mean by that is, if you have negative 2 and you square it, you're going to get 4. If you have 2 and you square it, you're going to get 4. So when you square root 4, you don't know if the answer is going to be 2 or negative 2, so you have to look at the problem for physics. And since she's falling downwards, we know that her vertical velocity, her final vertical velocity right here, is going to be negative, so this is actually negative 17. Question 16 reads, a large firework called chrysanthemum is launched straight up into the air with an initial velocity of 180 meters per second. How high will it be after 1.2 seconds? So, we're shooting up a firework. So our initial velocity in the y direction, because it's vertical velocity, is 180, and it wants to know how high it is, so delta y, after 2 seconds, or sorry, 1.2 seconds. So we're going to use delta y equals v naught t plus 1/2, get out of here, at squared. And for this one, we actually do have an initial y velocity, and it's given to us here. It's 180 meters per second. That means initially it's moving up, as opposed to the rest of the problems we've been doing, where initially it's just dropped. So 180 times 1.2 plus 1/2 a is negative 4.9 times 1.2 squared. And you just plug that all into your calculator, add it up, and you should get delta y equals 209 meters. Question 17 says the chrysanthemum reaches its maximum height when the vertical velocity is equal to 0. Duh, that's true for anything you're throwing up. How high will it get? So in this case, we're going to want to use our timeout equation because we don't have the amount of time it's going to take to reach its max height, because this thing's going to go up and then it's going to come down. Hopefully it's burned up by the time it gets back down, otherwise you're going to get smoldered hair. So we could technically calculate the time it's going to take to reach the top, but that's really obnoxious. So we're going to use timeout equation. So V final squared equals V initial squared plus 2a delta y. And again, this is only dealing in the this is only working with the vertical direction right now, because we're only assuming it's going straight up and straight down. I drew this kind of the way I drew this, you would think that it actually moved to the side, but that was just to show that it went up and down. We have no reason to believe it did that. It wasn't given to us in the problem, I mean. So V final, since it's at the top, is 0, and they even gave that in the problem, which is lame, because you can figure it out yourselves, equals 180 squared, plus 2a is negative 19.6 times delta y. So we're going to move this over. Negative 180 squared over negative 19.6. Plug it into your calculator, and you get, drumroll, 1653 meters. It's really high for a firework, actually. And then question 8 says, what will the height of the chrysanthemum be after 1.9 seconds? So this is really just the same thing as question 16. They're just giving you a different number. So you want to, and sorry, I should probably put 17 for this part. And then, okay, so for question 18, you really just want to take this and plug time equals 1.9 into it. So delta y equals 180 times 1.9 minus 4.9 times, we're running out of room, 1.9 squared. Plug that all into your calculator, and you should get delta y equals 324 meters. Question 19 reads, Molly and Karen are afraid to ask Miss O'Brien for help with a physics problem. Molly says, let's flip for it, and she tosses a penny in the air with an initial vertical velocity of 8 meters per second. How high will the penny get after 2 seconds? Or, sorry, 0.2 seconds. So she tosses a penny up. This is question 19. So, with the initial equals 8 meters per second, and it wants to know y when time equals 0.2 seconds. So this is actually pretty simple to pretty similar to the last problem, and also problem 16. We can do delta y equals v naught t plus 1/2 a t squared. So delta y equals v naught. We do have a v naught. It's 8 meters per second. Times 0.2 minus 1/2 a is negative 4.9, or plus, yeah, negative 4.9, 0.2 squared. Plug that all in, and you should get 1.4 meters. Question 20 says, what will the maximum height of the penny be? Sorry, I just hit my mic. Hopefully that wasn't too loud. So for maximum height, we really don't want to do anything dealing with time, so we're going to use a timeout equation, because we're just looking for biggest delta y. V final squared equals V initial squared plus 2a delta y. So our final velocity, our final velocity is 0 because it's at the top. Our initial velocity is 8 meters per second, and we're going to square that. We're going to get 64 plus 2a is minus 19.6 times delta y, which is what we're looking for. So subtract it over. negative 64 over negative 19.6. Yeah, so subtract it over, divide by 19.6, and you get your delta y, which is 3.3 meters. Question 21 says, what will the vertical velocity of the penny be after 0.3 seconds? Okay, so we're going to do velocity equals v initial plus acceleration times time, because they're giving us a time, they want a velocity at that time, and we know our initial velocity and obviously our acceleration because it's vertical, so it's just gravity. So velocity equals 8, our initial velocity, minus 9.8 times 0.3. Plug it into your calculator, add it together, and you get velocity equals 5.1 meters per second. Question 22 reads, Allison hits a golf ball with an initial velocity of 130 meters per second, wow, at an angle of 37 degrees with the horizontal. What is the initial vertical velocity of the ball? Time for trigonometry. So first we're going to draw our velocity vector, which is 130 meters per second. And then we're going to draw our angle with the horizontal, which is 37 degrees. And then I'm just going to trace this out a little so we have a little more space. And then you can make it into a right triangle. And we're going to split this velocity into its... You can split this velocity into its x and y components. And we're going to do that for both... Yeah, we're going to get both its x and y components. It's not asking for the x component till the next problem, but we're going to do it anyway. So it's asking for the vertical velocity, which is v sub y, which is going to be equal to, so we're looking for v sub y, and we need to find a trigonometric quantity that relates the hypotenuse, the side opposite the angle, and the angle. So if we remember, which is going to be sine, because if we remember sine is opposite over hypotenuse. So sine 37 equals vy opposite over 130 hypotenuse. So 130 times the sine of 37 is going to be equal to our y velocity. So you plug that into the calculator. Make sure your calculator's in degrees, not radians, or you're going to get something crazy. And you get 78.2 meters per second. And that's the answer to 22. 23 wants to know v sub x. It says, what is the initial horizontal velocity of the ball? And horizontal is x. So same thing, but different trigonometric function. So we want cosine because this is adjacent, and cosine is adjacent over hypotenuse. So cosine of 37 degrees equals Vx over 130, multiply it over 130, cosine of 37 equals V sub x. Plug that into your calculator and you're going to get 104 meters per second. Sorry. Question 24 is still on this problem, and it says, what will the horizontal position of the ball be after 1.2 seconds? So it wants to know, as she hits her, where do we want to do this? 24. As she hits the ball, it's going to make an arc. They want to know how far it's going to be after 1.2 seconds. And just in the horizontal direction. So all we need is our horizontal velocity, which isn't changing because it's not being accelerated. Technically it's being affected by air drag, but shh, we're not dealing with air drag. So this is going to be really simple. Delta x equals Vt, which is equal to, sorry, this is V sub x, our x velocity times time, which is this. So 104 times 1.2 seconds. Plug it into your calculator and you're going to get 125 meters. And question 25 says, what will the vertical position of Allison's ball be after 1.2 seconds? This is a little bit trickier, but not by too much. So this is 25. So for this, we want to find vertical position, and we do have time. Yeah, again, it's 1.2 seconds. Should probably put that up here. So, yeah, we're looking for the vertical position, which is y or delta y, whatever you want to call it, going to be equal to our initial velocity in the y direction times time plus 1/2 at squared. And we start plugging everything in. We get our initial y velocity, again, is this. Yeah, this should be initial. Because this is going to change because it is being accelerated, unlike our horizontal velocity. So this is 78.2 times 1.2 seconds minus 1/2 a times 1.2 squared. And you plug that all into your calculator, and if I did my math right, you should get delta y equals 86.8 meters. So that means after 1.2 seconds, this height is 86.8 meters. Gonna need a new piece of paper here, but question 26, okay, I guess I should circle this real quick. Question 26 is asking, what will the maximum height of the ball be? What will the maximum height of the ball be? I can't speak tonight. So for finding maximum height, we want to know when we want to know where it is when the velocity is 0. And even though when you think about a golf ball, you think it's maximum height, well, yeah, it's still sailing through the air, but for an instant, it's only moving in the horizontal direction, not the vertical direction. So we're going to use our timeout equation, focusing or dealing just with the vertical direction, or the y direction, up and down. So we're going to do v final squared equals v initial squared plus 2a delta y. And we just said our v final is 0 because it's the y velocity, sorry, yes, the y velocity or the vertical velocity is not changing for a short little instant in time, equals our initial velocity, which we said was 78.2 plus 2a, so minus 19.6 times delta y, and then it's just plug and chug algebra. This pen's dying too. I'm going through these pens like mad. Negative 19.6 equals delta y. Plug that all into your calculator, and you should get 312 meters, which is really high for a golf ball, I think, at least. And then the final part of this question, I believe, oh, and sorry, I should write this as 26, is question 27, and it says, how much time will it take the ball to reach its maximum height? So now we're going to use the other equation, which has time, or delta y equals v naught t plus 1/2 at squared, but now we have our delta y, it's 312 meters, equals v naught t, and we're looking for time. Actually, no. We could do it this way, but now we have the quadratic equation. We have to move this over and use a quadratic formula, and that's really nasty. So the easier way to do this is to just go velocity equals v naught plus at, because we know, like we set up here, that the velocity at the top of the ball's arc up here is going to be 0. The vertical velocity, at least. So 0 equals 78.2 minus 9.8 t. So I lied. You don't actually need this distance, this height, to calculate the time it takes. You could, but like I said, this is going to be a quadratic equation, and it just takes time. I mean, you can obviously solve it, but I don't want to. I'd rather do it the easier way. So then you divide these over, and you get time equals 8.0 seconds. Oh, wait. There is more to this question. Oh, boy. Question 28. How far will the ball have traveled horizontally during the time it takes the ball to reach its maximum height? Oh, boy. So let's analyze that a little bit. How far will it have traveled horizontally? Okay, so it's looking for delta x, because that's horizontal. During the time it takes the ball to reach its maximum height. So we just calculated that. This is the time it takes the ball to reach its maximum height. So basically it's asking for delta x after this time, after this amount of time, which is really easy because you just take your initial x velocity, which we said was 104. We calculated that back. Whoops. We calculated that back here. That didn't happen. So you just want to take your initial x velocity and multiply it by your time. So 104 times 8, and you get 832 meters. Now for the final part of this problem, question 29, it says, what will the total length of the shot be? So something you should know about projectile motion, when there's no air drag at least, so everything you're going to deal with, is that it creates a symmetrical path. So this part is going to be the same as this part over here. So we said this was what, like 832 meters? That means for the time it takes to get to its total height and then get back down is going to be the same. The x displacement from the start to its max height is going to be the same as from its max height to its end, because it's just a parabola. It's a squared function. It's the delta y equals v naught t plus 1/2 at squared. So it's going to form just the parabolas you used to graph in some way, in some math class, I mean. And you remember, if you remember back to that math class, I mean, granted these are really terrible drawings of parabolas, but you'll remember that parabolas had axes of symmetry, or axes of symmetry, meaning that they're the same on both sides, and it's the same is true for projectile motion because it's just a parabola. So that means the total length of the shot is just going to be double this. That was a bit of a long-winded explanation, I know, but it's a concept you should understand. So double this, 832 times 2 is going to be 1664 meters. Next question is question 30, and this is a hard question. Well, actually, it's 30, 31, 32. Yeah, 30, 31, and 32, and they're pretty hard. So we're going to start with 30, and since it's a hard question, we have a new color pen. No, I'm just kidding. My other pen was dying. So question 30 says, Nicole is throwing rocks off an 8-meter high bridge into the river below. She throws a rock with an initial velocity of 7 meters per second at an angle of 32 degrees with respect to the horizontal surface of the bridge. So this is combining the two different types of problems you've done so far. So far we've done projectile motion where it starts flat and it's just going. So far we've done projectile motion where it just goes up and then back down. And then we've also done projectile motion where it just starts flat and then goes down. Now it's combining it where she's up on her bridge, there's water below, and it goes up and then back down. So this is like, I mean, no, this is poorly drawn, but this is like half a parabola. This is, okay, so if you have a parabola, this is like half a parabola, this part. This is like a slice of a parabola. But then this is like some weird portion of a parabola that isn't half. So it's going to be a lot harder to deal with. Okay. This first part shouldn't be too hard, though. It says she throws a rock with initial velocity 7 meters per second, 30 degrees with respect to the horizontal surface of the bridge. What will the maximum height of the rock be above the river? So that means we need to calculate where up here, we need to calculate what this is. because we know that this is, what is it, 8 meters? Yes, 8 meters. So we need to add this to this, but first we need to calculate this. And of course we know at the top of our motion, our y velocity is going to be 0, so we're going to use our time-out equation, plus 2a delta y. So v final is going to be 0 because it's momentarily stopped in the horizontal direction, equals v initial. Okay, so to calculate our v initial, draw a triangle with our angle and the magnitude. So we need to right now we need to calculate the vertical component, or our y velocity. So to do that, we're going to use the sine because it relates the opposite to hypotenuse. So sine 37 equals vy over 7. So 7 sine 37 equals, what does it equal? 3.7 meters per second, which is our initial y velocity, which is what we're looking for here. So this is going to be 3.7 squared plus 2a is negative 19.6, not 9.6, delta y. So subtract it over. Plug that into your calculator and you will get 8.7 meters. Oh, no, sorry, 0.7 meters. And then when you add, so that's this distance, and it's asking for the total height above the river, which is going to be this plus this distance, and that's your 8.7 meters, which is the maximum height up here. Next question says, how long does it take the rock to reach this height? So since we know the velocity up here is going to be 0, we're going to use velocity equals v naught plus at, and this is vertical velocities. So the vertical velocity up here is 0 is equal to our initial vertical velocity, which is 3.7, minus our acceleration, which is gravity, times time, which is what we're looking for. So move this over, divide by this, negative 3.7 over negative 9.8 equals time, which is going to be equal to 0.38 seconds. This is 31. Our next question is question 32, and in my opinion this is the hardest question on the problem set. The question's asking how far will the rock travel horizontally before it hits the ground. So first thing for this is we need to calculate our horizontal velocity. And we know that, again, we're going to redraw that triangle. So our angle is going to be 37 degrees, and this is 7 meters per second, and we want v sub x. And the thing that relates the angle, the adjacent side, and the hypotenuse is going to be our cosine. So the cosine of 37 degrees equals our adjacent over hypotenuse, which is Vx over 7. So 7 cosine 37 equals V sub x. Plug that into your calculator, you get 5.9 meters per second. But now, to figure out how far it traveled horizontally, we need to know how long it traveled. And the easiest and the only, well, not necessarily, yeah, really the only way to do that is by dealing with our y components. So delta y equals v naught in the y direction, t plus 1/2 at squared. And we're going to solve for t, and this is going to be quadratic, and it's going to be annoying, and you're going to hate it, but you're going to have to do it, so deal with it. So delta y, and this is a bit confusing, because delta y is a bit confusing because it started on a bridge, went up, and then went back down, and we said this was like 8.7, but this, from start point to end point, the y distance between that is only 8, which is given in the problem. So that's the delta. It's the final minus initial. Actually, negative 8, I guess. It's the final minus initial. 0 minus 8. So delta y is negative 8 plus the initial y velocity, which we said was 3.7. Plus 1 half a, negative 4.9 t squared. Ooh boy, time for quadratic formula. Here's the fun part. So move the 8 over, organize it, negative 4.9 t squared. Plus 3.7 t plus 8. So quadratic formula, for those of you who need a little algebra refresher, is negative b plus or minus the square root of b squared minus 4ac all over 2a, which is equal to negative 3.7 plus or minus the square root of b squared. What's 3.7 squared? 13.7 minus 4ac. So 4.9 times 8. So plus 156.8 all over 2a. And just in case you're wondering where I get these numbers, this is a, the coefficient in front of the squared term. This is b, the coefficient in front of the linear term. And this is c, the constant. All over 2a, which is negative 9.8. Okay, so let's add these up. Take the square root. Wonk plus wonk. Square root is 13.1. So negative 3.7 plus or minus 13.1 over negative 9.8. So that's negative 3.7 plus 13.1 over 9.8, or negative 3.7 minus 13.1 over 9.8. So negative 3.7 plus 13.1 divided by 9.8 is going to give you divided by negative 9.8 is going to give you negative 0.96 seconds, which doesn't make any sense. We don't want a negative time, so forget that. Because quadratic formula is always going to give you two answers. Negative 9.6 would tell us when it hit down here, but that doesn't make any sense because it was it started here and it's going this way. It's not going down this way. So you have to just logically get your two answers and figure out which one makes sense. So we know it's going to be this one. So negative 3.7 minus 13.1, divided by negative 9.8 gives us 1.71 seconds. Thank God. That was annoying. But we're not done, because it wants to know how far the rock travels horizontally, which is just going to be delta x equals Vx times time. We just calculated our time, and our Vx is hiding here somewhere. Here we go. So this is going to be equal to 5.9 times 1.71. So 1.71 times 5.9 is going to equal to 10 meters. Holy crap, that's one heck of a problem. That doesn't look much like a 10. 0, 1, 10 meters. The next question is question 33, and it asks, what happens to the horizontal velocity vectors with typical projectile motion? And the answer is they stay constant, because your horizontal velocity is your v sub h or v sub x, and it's not experiencing any kind of acceleration. Technically, like I've said, there is air resistance, but we're not dealing with that in this class. So for our purposes, it's constant. So the answer is they stay constant. Question 34 asks, what happens to the vertical velocity vectors with typical projectile motion? So your vertical velocity vectors, whether they be this way or this way, are you going to be your v vertical or vy, whatever you want to call it? And the answer is they're accelerating downwards, because they're always experiencing acceleration due to gravity, which is a vector in the downward direction with a magnitude of negative 9.8. So the answer is they're accelerating downwards. Question 35 says, what is the initial horizontal velocity component of a projectile shot at an angle of 43 degrees with an initial velocity of 7 meters per second? So, trig time. Angle equals 43 degrees. And it wants the horizontal component, which are Vx, and this is 7. So what relates these three values? Cosine 43 equals Vx over 7. 7 cosine 43 equals Vx. Plug it into your calculator and you get 5.1 meters per second. And then the next question says, what is the initial vertical velocity component of a projectile shot at an angle of 43 degrees with an initial velocity of 7 meters per second? So basically it's just asking for the Vy in this same problem. So 36, last question. And what trig function relates the angle, the opposite side, and the hypotenuse? That's right, it's sine. So the sine of 43 degrees equals Vy, our opposite, over our hypotenuse, which is 7 multiplied over 7 sine 43 equals y velocity, which is going to, you plug this all into your calculator and you get 4.8 meters per second. Woohoo! We're done. That is one hell of a worksheet. I hope you found this video useful. And I hope I did a good job explaining all this. There was a lot of problems, and it's really late, so I may have rushed through some of them. If you need any help, or most importantly, if you see any errors, because I don't have an answer key to this, so I did it all myself, and I'm human just like you, so I do make mistakes. So if you catch an error, or if you think something's wrong, don't hesitate to ask me on Facebook, or if you have any questions, don't hesitate to ask me. I'll say in the YouTube comments below, but nobody ever comments. So, yeah, just ask me on Facebook. There'll be a link to the Facebook group in the description. And if you really need help with this, or it's just really not making sense to you, like the concepts, like the real basic concepts, or just you're really having trouble, ask me, and I can give you a private session on Skype and see if I can explain it better and in more detail. But I hope you found this video helpful, and thanks for watching.